today's DTM colloquium. It is my pleasure to introduce Sean Andrews, who is visiting us from the Harvard-Smithsonian Center for Astrophysics in Cambridge, Massachusetts. Sean got his Ph.D. working on submillimeter data and at the University of Hawaii in 2007, and did a really interesting work as part of his thesis on the incidence of disks around binary stars and single stars around disks around young stars, looking at how long they last and how much time we have available for planet formation, which of course, as you probably know, turns out to be not nearly as long as some non-Carnegie theorists would like for making their giant planets. So Sean's contributed greatly to the whole study of the evolution of circumstellar disks. After his PhD, he went as a Hubble Fellow to the Center for Astrophysics, and then they quite wisely put him on their staff in 2010 as an astrophysicist. So I guess we can all be happy that our tax dollars are at good work studying the evolution of circumstellar disks. So to my surprise, this is actually his first visit to Carnegie, but we're delighted to have him talking about some of the amazing work he's been doing with Alma and other instruments to image disks.
Thank you, Alicia, and thanks very much for having me. It is my first time here. I think every time I've run into you for the past decade, you're like, oh, you got to come to DTM. And I just have never made it, but it's great to finally be here. So I'm going to talk about something that I hope sort of connects across many different of your research paths here at DTM, and that's the evolution of solids and the disks that form planetary systems. I'm primarily going to talk about the astronomical observations of those things, but I'll try and motivate it with some of the current theory. But let me just start sort of at the basics. I like to start here and just say that disks are the material, protoplanetary disks are the material reservoirs for planet formation. It seems like a very simple thing to say, and most of you in this audience probably understand that. But I start with this slide because it's the one thing that I'm sure of in all of this science. And the reason for that is basically there's lots of pretty direct evidence. First, we have actual images of these flattened protoplanetary disks, and we know they're rotating around their central stars from HST. This is an image where you actually see the disk in silhouette against a bright nebular background. But before we had this, in the early 90s, for centuries, people have realized that the planets in our solar system are actually moving in a relatively narrow plane called the ecliptic. This is just an image of a conjunction of some planets from a few years ago. So you actually see it in our own solar system pretty directly. People have known this for a long time. And interestingly, I would say the most modern sort of measurements where we know that this is happening is you look at these multiple planet systems. These are the transits, the small dips in the light curves toward a nearby star, a relatively nearby star, from the Kepler telescope. And you actually see the same system actually has B, C, D, and E, 4 planets. And in order for these planets to actually transit the star, they all have to be in nearly edge-on orbits, right? So the coplanarity of this system is within a degree of edge-on for all 4 things. So you see that they all form in these flattened disk structures. It's just really to kind of set the stage of why we study the disks themselves observationally. So, all right, everything else is speculation. Not really, but when we try and understand the actual planet formation process, as you likely know by interacting with with Alan over the years, that the standard theory, the standard model for the formation of planets has some pretty serious efficiency problems. I'm going to sort of, I can't help myself switching back and forth between calling them timescale problems or efficiency problems, but they're effectively the same thing. And there are a number of different ways of posing this problem or looking at the timescale as a problem. But the one I'm going to focus on specifically for the solids is that it's actually not trivial to understand how you build what we call planetesimals, the building blocks of planetary cores or terrestrial planets. So the theoretical idea, there are many theoretical ideas for how this happens, but it's not actually obvious if any of them work and how to make them in these disks, right? So the buildup to sort of centimeter size scales, I'd say at this point, is fairly well developed, both theoretically, observationally, and in the laboratory. So these are actual high-speed camera measurements of collision experiments in laboratories, where you actually just take a bunch of silicate monomers and throw them at each other and see if they stick or what happens to them. But it's not actually clear what happens from when you get to about centimeter sizes to these much larger bodies that are needed to make planetesimals. And I should say in the standard theory for planet formation, what's called the core accretion theory, those calculations typically in the past have started with a gas-rich disk and an abundant population of planetesimals, large bodies that then make up planetary cores and then grow into giant planets or terrestrial planets. That has their own timescale problem, which I'm not really addressing here. So as I'll try and argue to you, the real key to this process is that these pebbles, and I hope I'm using I just recently discovered that there is a geological definition of pebbles, and that geologists use magnitude systems like astronomers, which is my favorite excuse now when people complain about astronomical magnitude systems. And they're base 2 instead of base 10. Anyways, these pebble particles are actually key tracers for 2 reasons. One is a physical reason I'll explain in a second, but more importantly is that this is the last size of a solid that we can directly observe astronomically outside of our solar system, right? You cannot detect larger particles. The light from those particles is very, very dim, and no facility now or on the horizon will all be long dead before anyone creates a facility that could directly detect emission from large solid particles. So observationally, they're the key, and that's good because we have some good facilities to detect them. But let me explain the physical problem and why solving that problem is important to the planet formation theory. So the key problem is that in the buildup of planetesimals is that the solids actually move. They're not static and sitting and rotating around the star. There's this process called radial drift, which probably many of you know of, but if you don't, I would advise you not to Google it because there's this kind of grotesque arm injury. It's either that or you got pictures of Fast and Furious cars. But anyways, this is called radial drift, and I'll explain the process to you. So this is just a simple force diagram showing you what's happening. You have a little parcel of gas orbiting the star. It's balanced by gravity inwards, rotation outwards, and then it has its own internal pressure support, right? And so in the standard model for protoplanetary disks, the temperatures and densities monotonically decrease as you get further from the star, right? And that's because the temperatures decrease because the heating is primarily done by irradiation from the star, so the further you are, the less heating you have. And the densities decrease because of the standard model of how you assemble a protoplanetary disk and how mass is transferred. So that means you actually have a negative radial pressure gradient in these disks. And that little bit of pressure gradient contributes some force, and that means that the gas is actually not moving in perfect Keplerian rotation. The deviation is small from Keplerian rotation. It's on the order of 1%. But it's not negligible. At some point, particles are large enough that they start to decouple from the gas. And when they get large enough and decouple from the gas, they actually feel that velocity differential. They feel a drag force from that velocity differential. The drag force saps their angular momentum, and they will spiral towards the pressure maximum, which in this case is the inner edge of the disk. So that's just sort of a generic feature. The sizes at which you start to see this decoupling are the pebbles, right? So when you get to millimeter, centimeter sizes. So this is just a simulation. This is a map of the pressure in this kind of scenario. So you have this smooth pressure disk with pressure decreasing with radius. And then this is the radial velocity of particles, right? The gas is actually shown on here too, but it's underneath the micron-sized particles. So when you're a small particle, you actually just are completely dynamically coupled to the gas, and you just do whatever the gas is doing, which is effectively nothing. But when you start to decouple, these centimeter-sized particles in the outer disk start trucking in towards the star. And these are kind of crazy units that even for an astronomer, but they're my favorite units because they're instructive for understanding the level of the problem of this migration. They're 8 astronomical units per 1,000 years, right? So at tens of AU, these pebbles are actually moving 10 AU in 1,000 years. Typical disk lifetimes are maybe 5 million, 10 million years. So you can see you really should deplete these particles very quickly, especially from the outer disk. And this is what you see here. This is the surface density as a function of radius of these particles. See, the micron particles trace the gas pretty well, but the pebbles are actually much more radially concentrated. So there's also sort of fundamental microphysics problems with drift, and that is that the large relative velocities of these streaming in particles could lead to destructive collisions, and the growth process needs to get bigger. If you fragment things, you're actually going in the wrong direction, and then you'll have a timescale problem for assembling. The bigger problem in the context of planetesimal formation is that the timescales are such that the drift speed, or the timescale for a particle to move away from its current location, is much shorter than the timescale for a collision to potentially grow. So once a particle decouples from the gas, it moves away before it can actually grow, and growth is effectively halted at that location to larger sizes. So there's a maximum size at a given location and time that's dictated by the drift, by whether or not that particle is drifting. Okay, so I just want to sort of highlight again what you probably have seen in these plots. There are a couple sort of key practical consequences that we're going to look for observationally of this solid migration. One is that you have size segregation as a function of radius in the disk. So the larger particles drift faster, and they'll be preferentially more concentrated towards the central star. And as you look further out, you should see, in a relative sense, more and more small particles. Right? So you can see that kind of here in this depiction. And if you also look at this and you compare the ratio, the mass ratio of pebbles, large particles, to the gas, you see that there's a pretty steep drop with radius. Right? You actually get very few pebbles at large radii, and you still have plenty of gas. Those are the two key sort of physical consequences that we'll get back to with observational tests of this. So the question is, what can we see observationally? I say astronomical data because, of course, there's an entire separate field, as you are no doubt familiar, that addresses particle evolution in disks from a meteoritic perspective. I'm not going to talk about that, but your colleagues are experts, if you're curious. Let me just explain what I'm going to focus on in terms of astronomical data. And that is microwave interferometry. So this is a sort of the short end of the radio wavelength spectrum. We say 20 to 700 gigahertz or so. And interferometry, because you actually need to resolve these disks that are pretty small on the sky. They subtend about an arcsecond at most in diameter. And in order to get sort of sub-arcsecond resolution, you need a radio telescope that is, on the order of a kilometer. You can't build that engineering-wise. And if you really want to resolve sort of AU scales in these disks, you need something that's on the scale of 15, 20 kilometers. So you can't build that, so you use an interferometer where you just sparsely sample the Fourier transform of the sky brightness, and you can reconstruct images at very high angular resolution. The nice thing about facilities, this is the Alma Telescope. Well, this is the Alma Telescope a couple of years ago in construction. There's many more antennas now. And this is high in the Atacama Desert in Chile, and this is the premier astronomical facility. Speaking of tax dollars, this is your tax dollars, a $2 billion ground-based experiment for which you paid 37.5% if you're from North America. But the nice thing that this can actually do is it can measure thermal continuum emission and resolve thermal continuum emission. And that thermal continuum emission at about millimeter wavelengths is coming directly from those millimeter-sized particles. So you have a direct tracer of the distribution of those pebbles that we're so interested in. And at the same time, as you'll see, we also have, literally with the same observation, you have access at very high spectral resolution to the pure rotational transitions of many different key molecules. This is carbon monoxide, and what you're seeing in each panel is a different set of projected velocities. So the changing pattern you're seeing is based on the rotation of the gas disk. You don't really need to know that from here. I'm going to talk purely about sort of the integrated emission from these spectral lines, just to get you an idea on the distribution of the cold molecular gas. So the continuum is going to be the focus because I'm talking about the solids in these disks. And historically, the nice thing about microwave continuum emission is that it's probably what astronomers call optically thin, which effectively means you're seeing light from each individual pebble. And then when you add it all up, you get some, if you have some special conversion factor, the emissivity of the particles, you can effectively count grains and then figure out the mass of in the solids. If you know something about the solids, you make some assumption or do some model that tells you the temperature of the solids and the column density, the line of sight density of the solids, that's sigma. So this is really interesting sort of demographically, like in the simple sense, because you can just add up all the light, the luminosity at these microwave wavelengths, tells you something about the mass in the solids. Right? There's some direct relationship, and the conversion is a little tricky, but so you can actually just observe a whole bunch of disks in a demographic sense and learn something important about them. So we've done this over many years, and what we see a few important things. I'm going to actually just show you two of them, only one of which is published at this point, because I think it sort of immediately pushes me to talk about the migration of the solids. But the first thing you should know is that the total masses, or luminosity in the microwave continuum, depends on the masses of the stellar host and the ages of the stellar host. Right? There's a lot of scatter in this diagram, but there's a clear relationship. The mean relationship is that the disk mass, the solid disk mass and the stellar mass are roughly linearly related. And the ages is even harder to figure out, but it looks like roughly that if you're twice as old, you'll have twice as little mass as you go on. So that's true. These are in sort of broad time bins, 1 to 3 million years in gray, 5 to 15 million years in purple. So a lot of this, what I was going to say is that there's one dex of scatter around the mean relation. A lot of that scatter could be age related, and they don't all have to evolve at the same rate either, right? But there's certainly lots of other things folded in there. They could have a broad diversity of different particle compositions and sizes and so on. But that is certainly one possibility. So we look in these broad age bins, and you see this shift of this relationship to lower masses or lower luminosities. So that's something certainly that's folded into one dex of scatter around that relationship. And the problem is, so you'd like to do this in many different time intervals. The problem is, there's basically no nearby clusters that are between 3 and 10 million years old, right? So it's difficult to actually do this, but this is what we have at this point, sensitivity-wise. But I mean, one thing that we were looking at in the context of this, which has sort of revealed something that I think is interesting, is maybe this is just related to the distribution of those solids, the spatial distribution of those solids, right? And the question is, do more massive disks preferentially have higher surface brightnesses, or are they bigger, or so on? So we've been doing a resolve survey. This is just unresolved photometry data of these things. And now if we look at the luminosity or disk mass as a function of the size of those disks, we actually see a pretty tight relationship. I was quite surprised by this. This is work being done by my grad student, who's, the reason this isn't published quite yet is because she's doing a fellowship right now in the White House, which she started in August and committed to a year as a civil servant. So this has been going a little bit slow, as you might imagine. But the trend is actually quite tight, right? So the mean relation is a little bit surprising. It's basically the mass or the luminosity goes as the radius squared, which we can discuss later if you're interested, but that's not really what you'd expect, even though it seems intuitively okay to you. If you actually measure the dispersion here, there's a small amount of dispersion, actual real dispersion outside of the uncertainties. But we actually think that that's entirely temperature related. And if you correct for the temperatures, the relationship stays the same, but it's statistically indistinguishable from having no extra dispersion aside from the uncertainties. And I said age dependent or wavelength dependent. That's not because these two purple points look different. It's just that we actually expect these to be age or wavelength dependent. I'll explain that, or hopefully it will become clear a little bit later. So we don't have a good physical interpretation of why this relationship exists. But this actually gives you a first look back at the migration problem, because you have some estimate of the size of the emission, and that size of the emission is telling you something about the spatial distribution of those millimeter pebbles in the disk. So this is the first thing we have related to the migration of solids. And if we take a huge suite of theoretical models from my former postdoc, Till Bernstein, and try and see at the mean age of this sample, which is about 2 million years, the best that those theoretical models can do to predict in this plane, this is what we get, right? So as I was telling you before, they tend to underpredict the size as at a given mass, or you can think of this in one way or the other, right? But they actually are off the correlation. And there's nothing that we can really do in the standard smooth model of a disk to actually make this happen. So I'm going to come back to this at the end of the talk, but this is just a manifestation of what I was saying before. It's that the models of radial drift in normal protoplanetary disks are too efficient. You deplete particles from the outer regions too fast. Well, so it depends on how you look at this, but that's exactly right. And this is actually a really tricky point, which I was hoping to avoid. But right, so let me come back to it at the end, because I think I have a better explanation of it once you've seen the resolved data. So the standard model for the migration of solids is actually a problem for two reasons. One is that just in the sense of being able to make planetesimals, it's very difficult to do that in a reasonable time frame, because basically you should have depleted all of your solids into the inner few AU in a very short period of time before we can observe these things. And the other problem is that the drift models are actually in conflict observationally with the size luminosity distribution. And that's actually been known theoretically for a while, way before there are observations, that you actually can't even get the right luminosities, which is what I was showing in that plot, for these things, because you don't have those pebbles distributed to large enough radii. Right? So I don't know if you've guessed the trick, right? The trick is that basically even at long wavelengths, you're picking up small particles left over from the outer part of the disk. You'll see that more clearly in a second. So the kind of questions that people have been grappling with effectively since this aerodynamic effect was recognized 40, 50 years ago is there something actually just wrong in the models? Like, is this not the right physics, or do we not understand why this is happening? Or are we just making some assumptions when we set up the theoretical models that are not well justified, right? And so we really want to know this question. When you look at the data and when you think about this, you have to ask yourself, is this migration of the solids even happening at all? What's the observational evidence for that actually to happen? There's plenty of theoretical predictions, but what is the observational evidence? And so now I'm going to focus on that. So if you'll recall, there are sort of two predictions that are completely related to one another, but I like to separate them because they're visually easier to see. One is that you have this radial segregation of pebbles in gas, right? So look at the red curve here showing the surface density profile of centimeter-sized particles versus the gas, right? So the expectation is that if you actually measure the gas distribution, say the size of the gas distribution in a molecular emission line, it should be much, much bigger than the size of the millimeter-centimeter continuum emission. That's just sort of a very easy prediction to test in some sense. So I've sort of characterized that as a line to continuum gradient as a function of radius. The other thing is that you have a radial segregation of particle sizes where you have larger particles preferentially more concentrated towards the star. So centimeter-sized particles are bigger than millimeter-sized particles in green, and so on and so forth. That is a little trickier and I'll explain why, but there's a direct test of this as well. So if you actually look at the emissivity for grains of different sizes, you actually see that the spectrum, the emissivity spectrum, which I'm showing here, changes. So this is the emissivity spectrum, and then these correspond to these different particle sizes. So in the microwave bands, right, they're basically power laws. The emissivity spectra are basically power laws. And larger particles are flatter. They have flatter emissivity spectra. And that's just because you have more emission by larger particles effectively contributing to the emissivity function. Right, so if you think back to the very simple relation of an optically thin emission from these continuum things, right, you have emissivity times the Planck function times some column density, right? So there's no spectral dependence of the column density, and everyone here should, from freshman physics, understand the frequency distribution of the Planck function, I hope, for some given temperature. So the spectral dependence of the emission is dictated by the emissivity of the particles, which is in some sense related to the size distribution of the particles. And because these emissivity spectra are roughly power laws, we know that we expect the surface brightness distribution to vary with wavelength as something like 1 over lambda to the some power, alpha. Right? So the idea is that you actually measure alpha as a function of radius in these disks. And what you should see is that alpha should increase with radius, right? And so let me just break down why exactly that is. But in the inner disk, you have larger particles, and you have a flatter emissivity spectrum. That means lower alpha. And as you get further and further out in the disk, you're dominated by smaller and smaller particle sizes, a steeper emissivity spectrum, a higher alpha, right? So alpha as a function of radius should increase. Now, you cannot just go out into the sky and measure a color, which is effectively what this is, right? So in principle, what we're actually doing is looking for some size wavelength relationship, right? And it's a little tricky, but this is what some model predicts. The size is a function of wavelength, right? So as you get to longer and longer wavelengths where you're preferentially tracing larger particles, you will see a flatter spectrum from those larger particles. And it will actually be concentrated in a smaller size. Yes? These models actually have the size evolution of the grains built in. They can't form planetesimals, so yes, that would contribute in a sense. And basically, if you have large particles, much larger than the wavelength you're observing at, so if you have kilometer-sized bodies, those effectively emit nothing, and that makes the spectrum look like alpha of about 2, which is the Rayleigh-Jeans limit of the Planck function. So you get no contribution from emissivity. I'll explain that in a second. But yes, large particles would make alpha go to about 2. Right? So the effects of basically drift and growth are folded into these models in that sense. And they both contribute in the same way as well. And so the shape of that distribution is affected by both things, right? So you'd have to interpret that as well. But, right. So we see these things directly in the data, right? So this top row of brightly colored things. Now, I sort of got myself into a mess trying to match color things over many slides, but hopefully you'll bear with me here. So these are measurements of the same disk at many different bands, right? So this is basically a centimeter wave continuum. It's very small, compact. This is a millimeter wave. It's a little bit bigger. Submillimeter, a little bit bigger. And then we look at the small particles. This is scattered light at 1.6 microns. And that's distributed very widely, as we'd expect, because it's well coupled to the gas. This is carbon monoxide gas, right? So you can see both those effects in this series of images. Technically, it's difficult to actually just make a plot like this and publish in this field, right? You have to actually quantify the size, because there's some tricks to your eye from spatial distributions. But what we really measure with the interferometer, and forgive me from delving into this, but this is basically what we call a visibility profile. So these are the amplitudes of the visibilities measured by the interferometer as a function of the baseline length. What this really is a Fourier transform of the surface brightness, the radial surface brightness profile. And so if you remember to your Fourier analysis class, when you have something that's actually really compact in the sky, right, like a little tiny point source in the sky, you would basically have the same power at all baseline lengths, right? It would be flat. So basically, like, wide things are skinny in the Fourier plane and vice versa. So actually, just by taking the data, you can see the different spatial distributions in the visibilities directly as a function of wavelength. So longer wavelengths tracing larger particles are more compact, as you can see in these images. And this sort of just illustrates that. It's actually quite a bit easier to see this effect in the visibilities than it is in the image, except for in this example, which is a good example. And if you want to model these data to try and work out how alpha, the spectral index, varies with radius, this is what you get. This is sort of the 2 sigma error bars from some model of this, some model inference of this. So in the inner part of the disk, you're down at alpha about 2, right? And so the assumption there is that you have very large particles. And as you get further and further in radius, you get to alpha about 4, which is what we see for the diffuse interstellar medium. So we're talking micron-sized particles are dominating the emissivity. Right, so you actually see this, these effects pretty directly when you have good enough data at high enough spatial resolution. And this is an example for a special disk, which is like scattered throughout this talk. It's called the disk around TW Hydra. And just for those of you in the know in this field, I'm not just showing this because it's the best case. In fact, we actually see this always. Right? So there's not tons and tons of data where we have this kind of information, but there's a couple dozen disks now and you see this effect always, right? So the line to continuum size discrepancy is pronounced, right? Sometimes it's actually, so in TW Hydra is a factor of about 2, sometimes it's a factor of 10 in terms of radial differences. So this is carbon monoxide and this is continuum for 3 different disks. And it's seen everywhere. I should caution you that actually quantitatively interpreting this is this line continuum discrepancy is quite tricky. You have to do some radiative transfer modeling to know for sure it's happening. And there are some kind of subtle and interesting chemical effects that can be tricky in that if you remove the large particles from the outer part of the disk, and those large particles are the sites of dense ice mantles of the volatiles that you're tracing in the gas phase, you can actually create a chemical effect where you might actually produce more CO than we'd see otherwise. I don't know, there's all sorts of tricky things. But we do think that this is actually only explainable by the radial segregation of the pebbles in the gas. I would say that these microwave color gradients, just in the continuum at different wavelengths, are a much more direct measurement. There's no real explanation of them aside from the growth and migration of solids. There's no other sort of alternative. I will say is the standard interpretation. And I will get back to a variant of that at the very end, which we're just sort of grappling with. But these are also pretty pronounced. These are all the visibility profiles of different things. And you see them everywhere. And I should note, this is pretty problematic if you ever want to measure the density structure of the solids, right? Because in principle, you can still do that, but it means you actually have to measure the continuum emission at many different frequencies to actually backtrack out how the particle size distribution actually matters. So I've said 2 things that are seemingly in conflict with one another. One is that demographically, it seems like these effects are too fat, too efficient, and radial drift doesn't work. And then when we look at the resolved tracers compared to the predictions, the observational predictions, I'm saying that they're actually in pretty good agreement in a qualitative sense with those predictions. In fact, those predictions were made decades ago, and only recently have we been able to actually figure out the right test for them and do them. And they're not bad. So the behavior of radial drift is actually how we would expect. Right? So I guess the way I would say this is that the physics is probably okay. Right? We sort of understand the aerodynamic effects that would make the particles migrate. They just do it too efficiently. Right? So there's a quantitative issue that we can't reconcile. So I think the physical model, at least in the broad sense, is probably okay. The question about the setup, the underlying assumptions in the calculations is probably not okay, and I'll explain sort of why. When this aerodynamic theory for the migration of solids was being developed, the solution already existed. Basically, these things were worked out by people like Whipple in the 70s, and they already came up with the solutions for this, not really appreciating that it was a problem yet, but just considering all possibilities. And so the one thing that we'd like to tweak to make all this work is the assumption, the underlying assumption that the gas disk is smooth, right? And so the hypothesis is if the gas disk is structured and not smooth, and I'll explain that, you might be able to actually, you're not actually slowing drift rates you're slowing drift rates globally by manipulating them locally, right? And so the idea here is that you have a local pressure maximum somewhere in the disk. It doesn't even have to be radial, but somewhere in the disk, instead of a global pressure maximum at the inner edge of the disk. So say this pressure maximum now is at this black thing, this black curve and this gray patch of gas. Then it only basically feels gravity and rotation. There's no radial pressure gradient because you're at a pressure maximum. And so that gas will be moving at perfectly Keplerian speeds and very happy. And a little bit outside, it'll feel that radial pressure gradient because the pressure is decreasing away from the maximum. So that pressure that dPdr is actually pointed outwards, and that parcel of gas will move slightly slower than Keplerian. It will create that drift effect, and particles will migrate in to the pressure maximum. And actually, the opposite thing happens just interior to the pressure maximum, depending on the distribution of the pressures. The gas can actually be moving at slightly super Keplerian speeds, and that actually will fling particles out. And so what happens is that you have a convergent migration of these drifting particles to the pressure maximum, right? And they will concentrate there and not move. I mean, they can diffuse out because of turbulence, but they're effectively trapped in a pressure maximum, right? And so here's sort of this sort of simple example manifested in this diagram again, where you have a maximum pressure and then very little pressure inside here. And you get this kind of more complicated looking radial velocity profile where if you actually identify where the pressure maximum is, it's here, you'll have particles migrating inwards and then they stop. And you have actually particles flung outwards and then they stop here. So here's the surface density profiles, right? So the assumption in this model that's different is that you have this gap in the gas surface density distribution. So this is an actual simulation of if you plunked a Jupiter-mass planet into a disk at 20 or 10 AU, what would actually happen. So the gas is from hydro simulations, and then you run these particle evolution models on top of it. And you can see the centimeter-sized particles are all trapped in the pressure maximum. In some sense, the smaller particles become trapped too, but they're also more widely distributed. So this example that I'm showing here was chosen for a reason, and because it looks a lot like observations of this weird population of disks called transition disks, which is a terrible, confusing name that makes really no sense. But in this, this is standard astronomer jargon. If it doesn't fit in category A or B, it's in transition between A and B. In this case, A has a disk and B has no disk. Very creative. But these are a population of disks where actually you see the continuum emission. So you see the pebbles concentrated in these relatively narrow radial rings where there's not much pebble, there's basically no pebble emission inside, in this case, something like 40 AU. So the entire inner region of the disk is cleared of pebbles, and there's not much stuff outside of it either. They've all sort of concentrated in. But if you look at the gas is sort of everywhere in this disk, right? And that's just the classical signature you'd expect at modest resolution of a local pressure peak. One large amplitude radial ring pressure trap in these disks. So in my mind, the multi-wavelength constraints on transition disks are just the clearest signature that these structures actually perturb the migration of particles. So the big problem is transition disks are, by definition, not common. This is not a general solution to the migration problem. Not everything goes through this transition disk phase early enough, if they all go through it at all. to actually affect the migration of solids in the general population. There may be 10% at ages of a few million years of the sources. So the simple solution is actually just what we're calling substructure disks, where you actually take these pressure peaks with smaller amplitudes and finer scales and distribute them throughout the disk. And this is a super trivial, simple example, seemingly, where you've just imposed a sine wave perturbation on the radial density profile of the gas, which creates these little pressure peaks. So you can see that here in the gray. They're actually pretty low amplitude, but they're spaced everywhere. And it has dramatic effects. If you look at the radial velocity distribution of the centimeter-sized particles, you see that same outward acceleration and inward deceleration of those particles to meet in the traps. And you get these really narrow traps. And the neat thing is that you get these centimeter-sized particles concentrated on small scales, but at high densities out to large radii, right? And so the typical resolution I've been showing you has been something like 20 AU. So that's like 5 beams across here. If you convolve that with a Gaussian beam 5 times, right, you basically see a smooth distribution in the data, and you wouldn't know that you're trapping all these particles in really fine little spaces, and that might explain exactly what we're seeing. So the key point is that, for this to work sort of generally, we have to have just been missing these substructures because they're small, right? They actually happen on a few AU scales. And if you want to talk about mechanisms, I'd love to talk about that at the end. But so this paper, this particular simulation came out in 2012. It's just a building on those original theoretical ideas and just seeing, could you actually do this with relatively low amplitude perturbations? That's why it's so simple. And I sort of was fascinated by this paper, but I also sort of chuckled. I was like, oh yeah, you're not going to have all these little tiny rings, disks. And then Alma measured started using its longest baselines to get few AU resolutions of disks. And sure enough, you start seeing little tiny rings in the continuum emission. So this is the HL tau disk. This disk was actually observed for engineering purposes, strictly for engineering purposes, for Alma's long baselines. So Alma's long baselines were basically built into the project in the early days for the specific purpose of looking for planet formation signatures in protoplanetary disks. And when they do the engineering runs to commission things, they seek community input to try and see what would be the best source to test against. And so HL tau was actually chosen because it had the precursor highest resolution image of a disk, and it was just smooth. It was sort of, 15 AU resolution. It was just sort of a smooth looking disk. And I distinctly remember the email asking me my opinion on if HL tau was an interesting science target. And I remember shamefully responding that it was a stupid science target because it's a very young source. It's partly embedded in an envelope, and no one's really interested in it from the disk and planet formation perspective. I also remember a colleague of mine coming down the hall and asking me if I'd seen this image yet, and I hadn't. And he's like, yeah, there's a bunch of rings. And I was like, that can't be right. And then sure enough, someone emailed me the image. I have to admit, my immediate reaction was like complete fascination. And then like 30 seconds later, it was just the sheer panic of realizing like everything is wrong. Everything I've ever done is wrong. Anyways, there's a couple interesting things that I want to take away from, for you to take away from this. One is this is what we call the brightness temperature profile. This is just a way of measuring the surface brightness, but it's physically informative in some sense. Because if the emission is actually optically thick, the brightness temperature should be roughly the same as the dust temperature. And if you look at these numbers, these brightness temperatures are sort of tens to 100, hundreds of Kelvin. And that's about what we expect in this disk. That suggests that emission could actually be optically thick and not optically thin, like we've always sort of assumed. And if you look at the spectral index as a function of radius, so this is two different bands that we've observed, you see a very interesting behavior. When you see these gaps or these depletions of emission, you see these big spikes in the spectral index, which is basically saying where you don't see a lot of continuum emission, it's saying that the particles have to be small if they exist in there at all. But where you do see the emission, the spectral index is low. It's on the order of 2 out to 40 some AU. right? And again, as we said, 2 could mean 2 things: planetesimals, very big particles, or optically thick emission. So if the emission is optically thick, all you're seeing is the Planck function. The Planck function at these long wavelengths goes as about nu squared. And then you get out to larger radii where the densities are lower. You still see the same kind of opposite effect here, where you see gaps, you see smaller particles. But this is not optically thick out here, right? So this was sort of the standard observation. And then last year, we went and did it for TW Hydra, which is the nearest protoplanetary disk to us. It's much older. It's 10 million years old. And it's basically face on. And you see the same kinds of ring structures, including a little depletion at 1 AU. So this is the highest resolution disk, highest resolution image of a disk ever taken, including with Alma, I think. And unfortunately, it probably always will be. And the reason is it's only 50-some parsecs away from us. So it's the same angular resolution as the HL tau data, but it's much closer. So we have an advantage. So this is sort of an AU scale resolution. You see these gaps. And what's new is this plot. This is being worked on by my graduate student, Jane Huang. So the brightness temperatures here are a little lower than we'd expect, but not dramatic, within a factor of 2 with what we'd expect. And this is 2, right? So basically everywhere we see emission out to 50, 60 AU, just like HL tau, looks thick. And where you see the gaps, it looks like there are small particles in there. So this is actually a really important development in how we interpret data. So anyway, you have high brightness temperatures, shallow spectra. That suggests to me that you're optically thick. You cannot rule out there being planetesimals and being marginally optically thick, which would mean there's a heck of a lot of planetesimals in those regions, but I have no objection to that. But the suggestion is that they're optically thick. So HL tau is quite clearly optically thick out to about 40 AU. I'd say the optical depth has to be like 10 or more. TW Hydra is a much more marginal case. The optical depth is about 1, right? Because the brightness temperatures are lower than should be possible in thermal equilibrium in this system. So now I want to revisit sort of the evidence here and just state that, all right, I don't want to do too much based on 2 sources, right? But it is sort of nerve-wracking enough to kind of consider this. And we have to reconsider what might actually be, how we might actually be interpreting the observations. So I'm again showing this size-luminosity relation. And here are these evolutionary models. But here's what the optically thick boundary would be is, right? So part of this relationship is you shouldn't make things over here. Because once you're optically thick, if you just add more stuff, you won't get brighter. Right? You're just at the temperature that you're at. In fact, if you add too much more stuff, you could actually get colder because you're shielding stuff. But, so this is still off this correlation, but you don't actually have to be all optically thick. As I showed you, if you're concentrated in these narrow structures where you're thick, and outside of that, in the gaps, you're thin, right? You have some sort of beam dilution effect. You have some sort of filling factor. Right? And if that filling factor happens to be a few tens of percent, maybe 30%, this optically thick boundary would go right through this relationship. So in that picture, the size-luminosity relationship is effectively saying there's a lot of small-scale optically thick substructures that are unresolved, and to distribute along that relation, it's just basically saying the brighter sources happen to be the sources where those substructures extend to larger radii for whatever reason. Maybe they are intrinsically more massive or not. So that's a pretty testable thing with enough high-resolution data. We'll actually see if that's true or not. It's just as likely in terms of these kinds of observations that you just actually do have some mitigation of drift. You reduce the pace of radial drift, and then these models can align perfectly with this thing. But in order to reduce the rate of drift, we think you have to introduce substructures. And if you introduce substructures, you probably are trapping enough particles that you get thick. So I'm not sure you can reconcile this completely with these models without hitting this optically thick suggestion. And if we look here at the spectral index, so this is the inferred data, and This is the spectral index as a function of radius. And so the red is an evolutionary model. Again, this is the gray spectral index distribution for TW Hydra, which is 10 million years old. And this is an evolutionary model at 1 million years. Does a good job, but again, you have this efficiency problem. And blue is basically what I put in there, where rings at the locations of TW Hydra convolve to the resolution of the data that was used to get the gray effects. So clearly in TW Hydra's case, these can be explained as optically thick rings with a modest filling factor. Right? So that's So that's super unnerving for a lot of radio observers, especially for the radio observers who are trying to do chemistry, because it basically says that if the continuum is optically thick and your molecules are forming at the layer below where the continuum becomes optically thick, you will have a depletion that might be hard to see, and you will always get a screwed up abundance distribution and so on, right? So that terrifies some of my chemistry-focused colleagues. But from a planetesimal formation view, this is really exciting, because in order to become thick in these narrow rings, right, in order to have high optical depths in these narrow rings, the amount of mass and solids in those rings is pretty high. It happens to be like super Earths of mass, right? And if you concentrate that much solids in that narrow of a region, some of the leading models for rapid planetesimal formation start to work, like the streaming instability, and you can even have direct gravitational collapse. It's possible to have direct gravitational collapse. So that's exciting, because it might actually be signaling where planetesimals are actively forming. So the last thing I want to say is basically I've based this all on 2 disks, but there are a lot of measurements starting to come out at high enough resolution, sort of 10 AU resolution or better, where you can start to see these substructures. And so far, every single disk that has been observed at 10 AU resolution or better shows evidence for substructures, albeit blurrily. And you see quite a diversity. You see things like rings, like we saw before. You see this weird theta thing. I don't know what that means. And then you see these nice spirals, right? So we don't actually know what's going on yet. And without knowing what's going on, it's very difficult to understand the physical origins of those substructures, but I'm happy to answer questions about the many theoretical ideas that have been proposed. But we're going to try and figure this out over the next couple of years, because we have what's called a large program with Alma, which is just a whole chunk of time for us to observe a large sample of disks at few AU resolution and try and come to some terms with what might actually be causing the substructures, and therefore what actually is going on inside them. So I'll just throw up some conclusions and leave it at that. Thank you.
Questions for Sean? So you showed 2 different plots of alpha for TW Hydra, the one that your student's working on, and then this smooth one. Are they the same?
They're not the same, but they are consistent. So this was inferred from the previous generation of data, not high resolution. This is sort of 20 AU, right? Yes. Yes. What?
Which looks a lot lumpier.
Yes, it's a lot lumpier. But basically, we've done this test. If you can, right? But if you convolve it, these peaks sort of go together and they go up. Yes. Yes. Yeah. So it has to be. It can't be distributed broadly, right? They have to be fine scale features.
So how optically thick do you think it is
So for TW Hydra, well, within a few AU, I don't know, right? But within, I'd say in 10, 15 AU, it's a few. It can't be much more than a few, because because at 10 AU, the disk is not 20 Kelvin or less, right? It's hotter, right? So that means that 1 minus e to the minus tau, that you can figure out what it is. Yeah. So there is a clear degeneracy with porosity. These models happen to use, 40% porosity or something like that. But you can choose different porosities. And that does affect the slope. Because basically, if your maximum particle size is in the pebble range, and then you change the porosity, you change the slope, because you lose that resonance, the me resonance, as you get away from compact spheres. But so the shapes of these profiles change and everything, but the underlying conclusion doesn't really matter. The one thing that hasn't been looked at in terms of observables yet is the sort of the Japanese group's model for having incredibly large but very, very porous aggregates. Sort of like 100-meter porosity of 99% aggregates. That's one other idea about getting around drift. But otherwise, yeah, things will change if you allow porosity evolution into them, but qualitatively. Sure, Scott can go first.
Two things about these ring structures. One is you don't think it have anything to do with ice snow line?
Well, you'll notice that I very carefully did not speculate on origins, but that is one idea. The problem is, all right, so the idea is that basically you have particles that have ice mantles on them, and as they drift inwards, they go through a temperature that corresponds to the sublimation temperature of some key volatile ice. So they pass through the CO snow line, and then that CO becomes vaporized, and then something happens to the solids. So people talk about this like that's one thing that can happen. But if you actually track this down, there's literally 4 different things that can happen. You can have a depletion or an enhancement at the snow line, or a depletion and enhancement inside the snow line, depending on what you actually think is happening to the particle. So it's not entirely clear if any of those work or which one is best or if they all work. But that is the nice thing about our sample for the large program, is that is the one thing that I think we can test, because we have a diversity of host stars and therefore temperature profiles in these disks. You'd expect to see the same features, whether they're big or little enhancements or whatever, at the same separations, because you can measure the temperature profiles of these disks. And then for the hotter stars and therefore the hotter disks, they should actually be further out than for the cooler disks. So there's sort of nice empirical tests for that, but it's not clear if that's what's causing it or not.
How many disks do you expect to
20. And plus there's another probably 10 floating around that will be floating around by the time that's done from individual studies. Yeah. I think Alan did.
I was going to make the point that your motivation for the talk is to try to understand how beryllium particles
So I think Alan has been reading my NASA XRP proposal surreptitiously behind my back. I completely agree with you. The leading interpretation in the literature from both theorists and especially observers, right, is that these rings are caused by planets, right? And it is true, you can make these rings even by relatively low mass planets, like super Earth planets, because the gas gaps in those that, from a super Earth is tiny, but because of that trapping effect of the particles, you can actually create gaps like this from something like Neptune or something like that, in principle, according to the theorists. But that does not solve the problem of how you made the planetesimals that made those planets in the first place. So, if that is the interpretation, if that ends up being the favored interpretation, that it's effectively dynamical interactions with companions, what that says to me is that there were substructures at an earlier phase in the disk that are unrelated, that basically enabled planetesimal formation very, very early, right? And then everything else after that has been standard planet formation, core accretion. And if you can make planetesimals in a couple thousand years, you're golden. And so there are some ideas for that, right? So if it's not outright global gravitational instability at the early phases, you could have a secular gravitational instability that does it as well. If you're sort of marginally stable, you can create ring structures that do that. And then there are all sorts of MHD ideas, right, where you have turbulent zonal flows that can concentrate things. That can happen at early times. So that is a really interesting possibility, and it would really sort of turn things on their head and say planetesimal formation must happen incredibly early and efficiently, and just the underlying idea of slow aggregation is wrong. Right? I completely agree. That's not something that people point out in the literature, but it's certainly something that at least we appreciate. There's a logical circle there that doesn't make a whole lot of sense unless you invoke an earlier generation of substructures. Right. Exactly, yeah. I absolutely agree, yeah. And this thing that does show spirals does seem to be young, right? It's still embedded, still pretty deeply embedded in the Oaf clouds, right? So yeah, it certainly makes a lot of sense to me. The lower right one is HD 163296. It's an isolated A star that has, a bunch of rings as well. So actually, several of these three will be redone at 10 times better angular resolution in our program. So. The pig snout is AA tau. I called it a theta, but I like pig snout.